The members of the noble gas family are very non-reactive and form very few compounds because their electron arrangements are very stable. Many atoms gain or lose electrons to end up with the same number of electrons as the noble gas closest to them in the periodic table. For example, a sodium atom likes to lose one electron so that it can have the same number of electrons as the neon atom. When a chlorine atom gains one electron, it ends up with the same number of electrons as argon. So the periodic table is very useful for remembering the charge of ions, especially those of the elements on the left and right side. For example, on the left side, the group 1A elements, the alkali metals, they all form 1+ ions. The group 2A elements, the alkaline earth metals, they all form ions with +2 charge. On the other side, group 7 elements, the halogens, they form ions with one negative charge. The group 6A elements form anions with 2 negative charge. However, as we're going to see later, many of the other groups don't follow such simple rules. A great deal of chemical activity involves the transfer of electrons from one substance to another. This figure shows that when elemental sodium is allowed to react with elemental chlorine, an electron transfers from a neutral atom to a neutral chlorine atom. Now we have a sodium ion and a chloride ion, which bind together to form the compound sodium chloride. So this is an example of ionic compound, a compound containing both positively and negatively charged ions. We can often tell whether a compound is ionic or molecular. In general, cations are metal ions and anions are non-metal ions. As a result, ionic compounds are generally combinations of metals and non-metals, as in sodium chloride, or it should be L here. Molecular compounds are generally composed of non-metals only, as in H2O. The ions in ionic compounds are arranged in a 3-dimensional structure. It's kind of a network, as you see here for the arrangement of sodium ions and chloride ions. Because there's no individually separate molecules of sodium chloride, as in H2O, we can write only an empirical formula for this substance. Now, if you look closely at this network, each sodium ions is surrounded by 6 chloride ions, 1, 2, 3, 4, and then 5, another one behind it, and then 6, another one in front of it, but it's not pictured here. And likewise, each chloride ion is surrounded by 6 sodium ions. So the empirical formula is NaCl. In fact, only empirical formula can be written for ionic compounds. Here is an exercise. We can write the empirical formula for an ionic compound if we know the charge of the ions. The ratio of the ions in an ionic compound are always such that the total positive charge equals to the total negative charge. For example, the ionic compound formed from magnesium, which give you the magnesium cations with +2 charge, and chlorine, which forms the chloride anions. The ionic compound formed from these two elements is MgCl2. Now let's look at the naming of ionic compound. For the positive ions, the cations formed from metal atoms have the same name as their metal. So sodium ion and ions formed from zinc is called the zinc ion. From aluminum, you have aluminum ion. And ions formed from a single atom are called monoatomic ions. If a metal can form different cations, then the positive charge is indicated by a Roman numeral in parentheses following the name of the metal. For example, iron can form two different cations. One has a 2 plus charge and the other has a 3 positive charge. So you indicate the positive charge by a Roman numeral following the metal. And same with copper. Copper can form copper ions with 1 plus charge or copper ions with 2 plus charge. Most of the metals that can form more than one cations are the transition metals from group 3b to group 2b. Their charges are indicated by, as we said before, Roman numerals. The metals that form only one cation are those in group 1a, such as sodium, potassium, rubidium, and group 2a, such as magnesium, calcium, strontium, barium, and aluminum in group 3a, and two transition metal ions, the silver and zinc. An older method of naming when a metal can form different cations is to apply the ending OUS or IC for the lower and higher charged ions, respectively. They are added to the root of the element's name. These two ions are the only ions of this kind we are going to see in the text. The ferrous ion and the higher charged ferric ion, or the cuprous ion and the cupric ion. The names and formulas of some common cations are shown in this table. Now for the negative ions, the N-ions, the names of monoatomic N-ions are formed by replacing the ending of the name of the element with "ide." So if the N-ions is formed from hydrogen, then it's called hydride ions. If it's from oxygen, it's called oxide ions. If it's from nitrogen, it's called nitride ion. A few examples of polyatomic N-ions also have names ending in "ide." For example, you have hydroxide ion, cyanide ion, peroxide ion. Polyatomic N-ions containing oxygen have names ending in "ate" or "ite." So these N-ions are called oxy N-ions. The ending "ate" is used for the most common oxy N-ions of an element. The ending "ite" is used for an oxy N-ion that has the same charge but one atom fewer. For example, the most common oxy N-ion of nitrogen is nitrate ion, NO3, and that is NO3 with one negative charge, and the nitride ion is named for NO2 with one negative charge. And prefixes are used when the oxy N-ions of an element have 4 members, as with the halogens. The prefix per indicates one more oxygen atom than the oxy N-ion ending in "ate." The names and formulas of the common N-ions are listed in this table. Those N-ions whose names end in "ide" are on the left side. Those whose names end in "ate" are on the right side. The most common ions are in boldface. So the name of the ionic compound consists of the cation name followed by the N-ion name, as you see here. Just to summarize the naming of ionic compounds, for the cations formed from metal atoms have the same name as the metal. If a metal can form different cations, then the positive charge is indicated by a Roman numeral in parentheses following the name of the metal. And for the N-ions, the names of monoatomic N-ions are followed by replacing the ending of the name of the element with "ide," and then you have a few examples of polyatomic N-ions that also have names ending in "ide." You need to remember these. polyatomic anions containing oxygen have names ending in -ate or -ite. So these are called oxyanions. Anions derived by adding a hydrogen ion to an oxyanion are named by adding the word hydrogen or dihydrogen. For example, here you have an oxyanion, a carbonate ion. When you add an hydrogen ion to a carbonate ion, then you get a hydrogen carbonate ion. For our present purpose, an acid is a substance whose molecule produce hydrogen ions when dissolved in water. At this stage, the chemical formula for an acid will be written with H as the first element, as in HCl and H2SO4, hydrochloric acid, and sulfuric acid. Acids are named in a special way. The name of an acid is related to the name of its anion. Here are the rules for naming acids. Acids containing anions whose name end in "ite" are named by changing the "ite" ending to "ic" and adding the prefix hydro. For example, the acid containing the anion chloride has a name called hydrochloric acid. So you change the chloride to chloric, and then you add hydro before that. The acid hydrosulfuric acid. It has the anion sulfide, so the corresponding acid is called hydrosulfuric acid. Acids containing ions whose names end in "ate" or "ite" are named by changing "ate" to "ic" and "ite" to "us", and then adding the word acid. If the anion is chlorate, the corresponding acid formed from this anion is chloric acid. The procedures used for naming binary or two-element molecular compounds are similar to those used for naming ionic compounds. So this is how you name a binary or two-element molecular compounds. The name of the element farther to the left in the periodic table is usually written first. An exception to this occurs in the case of a compound containing oxygen. Oxygen is always written last. Except when combined with fluorine. If both elements are in the same group in the periodic table, then the one having the higher atomic number is named first. The name of the second element is given an "ite" ending. Greek prefixes, as you see in this table, are used to indicate the number of atoms of each element. The prefix mono is never used with the first element. For example, if you have a binary molecular compound formed from these two metals, nitrogen and fluorine, because nitrogen is farther to the left in the periodic table, so you name nitrogen first, and the name of the second element is given an "ite" ending, so it's called a fluoride. You change it from fluorine to fluoride, and then you use the Greek prefix tri here, so it's called nitrogen trifluoride. And with the dichlorine monoxide, because oxygen is involved, so oxygen is an exception. It is always written last. So you call it a dichlorine monoxide instead of oxygen dichloride.